I'd like to welcome all of you to the second installment of Science Saturday for 2026. I am Joe Zehnle. I'm going to be, I appreciate you coming out on Valentine's Day, okay? But it's a wonderful way to start a romantic evening, I think. Or at least, right? At least that's what I kept telling my wife, and she was like, yeah, right. So we're going to talk about, wait a minute. So last Saturday, if you guys were here, you saw Professor Ozpolat talking about the sexual and asexual reproduction of worms and their mating habits. So somehow I think that that's more appropriate for Valentine's Day than this is. But hey, they didn't listen to me, so all right. So the theme of this semester is predicting the unpredictable. Keeping with that, I'm going to do probabilities in quantum mechanics. But I'm not going to get into any of the weird stuff. You know, you guys have probably heard about teleportation, spooky action at a distance, and all these other weird things in quantum mechanics. I'm going to stay with pretty much fundamental quantum mechanics and how you go about doing things, right? I'm going to show equations. I'm sorry. I apologize up front. You don't have to know them. If you don't like them, ignore them. But I'm going to do them at a pretty high level. So it's going to be more of an intuitive understanding of some of these equations and a little bit of a history lesson at times too. So I'm not going to get into details of them. Don't let the equations scare you. We're going to really talk about something called spin 1/2 and how universal it is. So it's a lot of places you're going to see. And it surprisingly shows up in places where you wouldn't expect it. So the math at least is the same. Going on to, so like I say, there's a lot of equations. That means, and equations tend to be abstract. People tend to get, too many equations. Don't let that bother you, okay? Abstractions are a good thing and they're a bad thing. They're a good thing when you have abstractions, like old Al took Newton's laws of gravity and generalized them. We'll come back and try this. I'll keep fiddling with it. Old Al took Newton's laws of gravity and generalized them essentially for general relativity. So abstractions are good in that sense, in that you're pushing the boundaries of knowledge. But they're also bad because when you go in and you try to learn it the first time, you're like, what the hell is this thing? I don't know what this thing is. All these crazy symbols written on a page. Hopefully we're going to make these things more concrete and more approachable to everybody. The noted psychologist Steven Pinker at Harvard has examples. If you take the same problem and change the names, you got Peter, Paul, and Mary, and you change the names to A, B, and C, and you call it abstract, most people fail. But if you take that same problem, you go back to the original thing, everybody gets it right. So abstractions really confound people at times, and all I can say is fight your way through the abstractions, figure out how to translate those abstract concepts, those abstract variables back into things that you're familiar with. And if I'm not doing that here, then there's a problem, but I think I will. So at the end, I got a bunch of demos to show you, which I think is the fun part. It's nothing's going to blow up, no explosions, nobody gets maimed, but I still think they're interesting because they're going to add some physical credence to what I'm showing you, all right? And I apologize that there are some pages with math in this stuff. You can't get around it if you're trying to explain it. I want to really show you the flavor of what people do when they go through quantum mechanics. So, let me just make sure I got everything going here. Stephen Hawking once wrote that for every equation he puts in his books, it halves the number of sales. So for every equation that I show here, I expect half the audience to go, and then the next equation, another half go, and another equation. But you're going to stay, or you're going to stay with me, aren't you, sir?
Yeah.
Okay. What's your name?
Stan.
Stan, you're going to stay with me the whole time. Thank you. So I'm counting on you. Okay. This is the first wave function that I wanted to show you. This is the simplest wave function in quantum mechanics. This is a free particle. And what you're seeing, get my mouse. There we go. Mouse is working. Okay, so all the blue stuff on the inside is the wave function, and we call it psi. Sorry, it's a Greek letter. It's just a number. It's just a function, and it's a function of position and time. And if you plug in position and time, you get a number out of it. That number's complex, but I'm showing it as like a sine wave, and it has an envelope. So if this function represents a particle, so the particle is most likely to be at the peak in here, but it doesn't have to be. It could be anywhere in here, and then outside of this packet is a zero. And the outer envelope is not really there, but it's kind of there, right? You can see it. I just drew it in here just so it's obvious, but it doesn't really have to be there. How do I get probability out of this thing? I need probabilities. I need to know where stuff is. Well, that's the next picture. So it comes back, it's a thing called the Born rule. Max Born said that probability is psi squared. That's that previous thing, squared, but it's not just squaring it because it's a complex number. I'm going to get into what complex numbers are in a second here because I don't think everybody knows, but you can't just square it. So if I take like -5 and square it, I get plus 25. That's simple, but you can't do that with a complex number because you got this other piece to it. So you have to do psi dagger psi when you're trying to calculate this thing squared. So the particle, and I like to think of a beach ball here, it's smaller than the whole packet. So the peak is the expected position of the particle, and we write that expected position as angle bracket x angle bracket. The x is the operator that says, hey, give me the position of the particle. X operates on the wave function, and really the wave functions are there. We just normally don't write them. You put a psi on either side, and then you have to there's a dagger in here, and then the spread of this thing is the uncertainty in the position. Now notice there's nothing here below 0. That's because I squared it. So -5 squared is like plus 25, so there's nothing below the 0 line anymore. That's what you want when you square it. That's part of the reason for squaring it. Again, this is a complex number. It's not a real number, and I'm going to show a little bit more about that in a second here. So, pardon?
If you square a complex number, you may not end up with a positive number.
I'm going to show that.
Okay.
It's coming up. Didn't forget about you here. So again, the Born rule probability is psi squared, which is really psi dagger psi. The height of this thing, the height of psi squared, is that's the expected position of the particle. But the number of zero crossings, that is the frequency, is the momentum or the velocity. So how close these things come together down at the bottom, that tells you about the velocity of the particle. And in this case, they're all uniformly spaced, so it's a uniform velocity throughout it. A little bit more on the notation. When we write angle brackets around the x, and x is not just a simple variable, it's an operator, but we're not going to get into operator stuff too much. We call the thing in the middle the operator. The thing on the right is called a ket, and the thing on the left is called a bra. So we are going to explore that a little bit more, and I'm going to show you just a little bit of detail on how we do this stuff, but not too much, because I don't want to bore you guys too much with all that stuff. So, did I skip a slide? Nope. Okay. Complex numbers. I hate the name. I really do. It was actually, the name complex and the name imaginary numbers, I don't know if you guys have heard about them before, they were actually derogatory names back in the, before the 1500s. They were mathematicians who believed in imaginary numbers and mathematicians who did not. Stan, do you believe in imaginary numbers?
Yeah.
You do? Okay, good. So they were derogatory terms. I don't think they're good terms. I think there's another set of terms that'll help you understand it and realize that these things really aren't that mysterious. So I want to start here with Euler's fabulous formula. E to the I theta cosine theta plus I sine theta. This has been, whole books have been written about this one equation. It is at the heart of almost all your electronics today and lots of other stuff. It's in your cell phone, it's in the GPS, it's every place. So this one formula right here, I know it looks mysterious, it's really not that bad. So if you exponentiate, E is 2.71828, I is the square root of -1, theta is just some angle, got to measure it in radians, and then you get cosine plus I sine. I take the whole thing, I multiply it by r, and then I call r cosine the x-axis, and I call r sine the y-axis. And if you put it with y, you call that the imaginary number. So another notation that people use is r at an angle of theta, or r at theta. These are both polar coordinates, and we're used to Cartesian coordinates, right? So if I measure 5 inches over, or let's say 12 inches over and then 12 inches back, that gives me a new point right here. So let's say this guy's at that point. But I could also measure, call this my origin, I could also measure the magnitude to that thing. So it's about 15 inches. And then, but it's at an angle of about 30 degrees. So there's two ways to represent any point. And that's all this is saying. So don't let that bother you. And people realized a while ago that complex numbers act like two-dimensional vectors. So you have an x and a y, but no z. There's no third dimension to complex numbers. It's only two dimensions. And mathematicians like to write that as c is an element of real squared. That means complex numbers are made up of two real numbers. And this book here, if you've had one semester in calculus, one semester you can read this book. Paul Nahan has a bunch of fun books to go read. The opening preface in this one is, "When did math become sexy?" Okay? And he's got a lot of good stories. He's got a good sense of humor. And if you can handle the first semester of calculus, you can read this book. It's really all about Euler's equation here. And this is at the heart of complex numbers. So, but it's also at the heart of how your cell phone receives messages, how your Wi-Fi works, how GPS works, and many, many other things. We use this all the time, daily. You get to the point where you even forget you're using it at times. So, all right. So here, again, what I'm explaining here is just that polar coordinates are identically to Cartesian coordinates. I got the same origin. I got the same point, and you can think of these two pictures on top of each other, and it's just a way to convert between Cartesian coordinates, x's and y's, and polar coordinates, which would be like magnitudes and angles or radiuses and angles. The first person to really visualize this stuff was Argon, and he lived, I think 1700s. He lived just after Euler, and he was like one of the first people to start to really visualize complex numbers, and they call it out an old name for the complex plane. That is what we're looking at here, this complex plane, because you got x's and y's, is the Argon plane. And my estimation is that's when complex numbers really started taking off, is when people are able to visualize them. You know, if you go back, I was reading in Derbyshire's book that the Egyptians knew that you couldn't take the square root of -1. But they thought it just meant stop, don't do anything, you're done. But that's not true, as shown later by a guy named Bombelli, but that's another story for another day. So visualizing complex numbers on the plane will help you a lot. And when you realize that these are just a way to plot things, or maybe like two-dimensional vectors, I think it's easier to understand them. So I have always hated the name complex. I've always hated the name imaginary. The co-inventor of calculus, Leibniz, he used to call imaginary numbers the in-between of being and not being. So mathematicians were skeptical of them too for quite a long time, until people started really proving theorems with them and started showing that complex numbers work. Complex numbers are in all this stuff. We have to use them, but I don't like these terms. I would prefer real numbers be called horizontal numbers and imaginary numbers be called vertical numbers. And you put the two together, they're just called doublets. I think that would be a much better name. It's a lot less mysterious, right? So, oh, okay. And then I like the suitcase analogy. So put horizontal numbers in one side of the suitcase, put vertical numbers in the other side of the suitcase, and then the hinge that goes down the middle is the separator. It's the I, it's the square root of -1 that keeps the two separated. As the name implies with doublets, there are things past doublets. All right, well, you've probably seen 3 vectors, which are x, y's, and z's, but there's also things, quaternions are really the next ones past this. And quaternions are quadruplets. They're 4 real numbers put together in a special way. And then it goes on, octonions, past that. So there's actually mathematicians out there, or physicists really. John Baez out of the University of California, Riverside, is a big proponent of using octonions for stuff. But that's well beyond this scope here. I'm just letting you know that they fall into a ladder. Doublets, quadruplets, octets or octonions, and so on. They keep going on. So complex is just the place to begin with it, but they're not mysterious. You know, you can't take the square root of -1, but we can imagine what it really means. And what it really means is a rotation of 90 degrees. So if you're a horizontal and you rotate by 90 degrees, now you're vertical. That's really all that I is doing. It's a rotation. So here's a fun little fact down here. Plug in e to the I pi. Again, you got to work in radians. And cosine of pi and sine of pi. So you get a -1 plus I 0, which is -1. Take the -1, move it back over to the other side. You get e to the I pi plus 1 equals 0. When I first saw this, I was like, wow, I take it back. When you first saw it, I'm just like, okay, it's an appendix in a book. I didn't think about it. Then, after reading several other books, Derbyshire's book being one, I don't have a reference to his, I'm sorry. You now just put the 5 most important constants in all mathematics in a single equation. And it's so simple. E raised to the I pi plus 1 is 0. That's really, I mean, you don't see that very often. And here's some just examples of different complex numbers. So I can say A is 5 plus I6. And now notice I put this in angle brackets, but there's a comma in the middle. So apologize, this is not my notation. This is other people's notation. So if you see an angle bracket with commas, which you won't see in this presentation except for here really, then it's a list. It's a vector. But if you put angle brackets and there's no commas in it, then I'm doing an expectation value. So again, psi is a function. Psi is a function. And if I stick in a particular position and a particular time, then I'm going to get out a number, 11, 22 in this case or something. I'm just making up numbers here. That's not properly normalized, by the way. We're not going to worry about normalization. It's tedious. It's not all that useful for what we're doing today. So let's go. Here you're asking the question about squaring it. This is busy. I totally agree. This page is busy. Don't read the details. But if you just take c squared, I got c as a plus ib. And again, the mathematician's notation is a comma b is an element of real. They use the hollow letters, is what they call them. R means it's real. These are real numbers, 5 and 6. All right? But c is an element of complex, which is real squared. And that's the way they write it. It's just shorthand notation for when you're looking in books. But if I just take c times c, and I use the regular old FOIL technique that you learned maybe when you were a wee little tot in grade school, is that you multiply all the terms out. If you just do this, you get the wrong answer, minus 11 plus I60. That's not what we want. So we do it this other way. C squared is c dagger c. And see, dagger is funny. The dagger is two things. It's two operations. The conjugate's the important one here. It says take the plus sign and turn it into a minus sign on the imaginary part only. So I turned a plus IB into a minus IB. And then you multiply it out, you get a squared plus b squared is the magnitude squared, which is the radius squared. This is what we really want. And a quick example is that the imaginary terms in the middle cancel out and you end up with 61, which is the right answer. That's squared, by the way. So that's what we really want. That's why we do the dagger. So C dagger C is a right way to calculate magnitude when you're dealing with complex numbers. And really what we're doing here is if I give you an x and a y and a Cartesian coordinate, you square them, add them up, and then you take the square root and then you get the magnitude. Well, this is just the radius of the circle. This is the hypotenuse that you learned a long time ago. So it's nothing more than that. But that's what we want. That's why we do C dagger C. The transpose is not important yet. We're going to learn about it later. It's really not a big deal. We've got column vectors, row vectors, matrices, scalars. I know it's a plethora of terms. And it's when you're learning this stuff for the first time, this is all matrix algebra, or today it's called linear algebra. You got to learn it, and it was forced upon physicists a long time ago. They didn't want it at first. So matrix algebra and stuff like that, but they learned we have to deal with it. So if that was the real part, if that was the magnitude, what's the theta part? Well, the theta part, and I'm not going to go through all the calculations here because it's just too much. So if I say C is A plus IB, again, A and B are real numbers. What is E raised to the ICT? That's this C here, and T is time. So if I do that, I get, again, our old friend, Mr. Euler's fabulous formula, cosine AT plus sine of AT, but then it's times e to the minus bt. So it's this cosine and sine part that does all the wiggling. This is the thing that's oscillating. This is the thing that's wiggling. It's this other term here. If b is positive, this thing decays. That's what you're getting. So the sine wave in here that's going up and down, and then the envelope is decaying away. So this is like the decaying, so if you got like a probability curve, so the probability can be shifting from one point to another point, and it's these exponentials that are moving things around on you, basically, if you want to think of it that way. If b is less than 0, then you get exponential growth. So really, the theta part is the y, is arctangent of y over x. In this case, it's arctangent of b over a. In general, it's arctangent of the imaginary part over the real part. So the theta really tells you how much is it growing and how much is it decaying. This is not the only interpretation of this stuff, by the way. This is just one. So you can use complex numbers in different ways, but this is one way you use it. So if I hit a light switch or something and I turn something on, I might get if I turn lights on, I get an exponential growth and then it settles out. Or if I turn a light switch off, I might get an exponential decay like this. So that's kind of related to that stuff. Again, the theta part is kind of telling you how much it's going up and down. So there's a physical interpretation to these things. It's an eyeful. Don't worry about it, all the details. What I want you to show you is, first of all, Bras and Ketz. If you put them together in an integral, you just get, we want it to be 1.0. It doesn't necessarily equal 1.0. We have to do something to it to make it come out to be 1. This is normalization condition, and I'm going to ignore it for this stuff. Okay? It's there, but I'm going to ignore it. We want it to always be 1 because now I want to start asking questions about particles. What's its position? What's its momentum? Linear momentum. What energy does it have? What angular momentum it has? And there's two different kinds of angular momentum. There's orbital angular momentum. That's like the Earth going around the sun, summer, winter. And then there's the Earth spinning on its own axis like day-night rotations. That's just called spin a lot of times. Spin angular momentum, SAM, or just for short, we just call it spin. Orbital angular momentum, a lot of times they'll write OAM, or we'll just say angular momentum without the orbital. I apologize, this is the terms, but you just sandwich the operator in between the wave functions. Again, the wave functions are telling us about probabilities. The operator is operating on the wave function to the right, doing something to it, and then you're putting them together and you're asking about what the expectations are. I'm not going to talk about how they're spread out and everything. It gets way too complicated, way too detailed. So no spreading, no Heisenberg uncertainty or anything like that. I apologize, this is really sounding, it gets a lot more visual later, okay? It's a little bit of mathy right now, you know. So here's Schrodinger. How does the wave function come about? Well, it's Schrodinger's equation, all right? Schrodinger's equation, the first time I saw this, I'm sitting there going, what is that thing? How am I going to memorize this thing? How am I going to know what this thing does? Well, it's actually, after a while, you get used to it and you kind of figure it out. But it really is nothing more than total energy equals kinetic energy plus potential energy. That's pretty nice. That's something I think most people are familiar with, potential energy and kinetic energy. And then this V of x, this is your potential energy. I haven't put it in yet. It's generic right now. If it's 0, it's a free particle. That's like the one on the first page. So, but I like to think of a golf course whenever I'm thinking of potential energy. So you got a ball at the top of a hill and it rolls to the bottom of the hill. Unless you play golf like me and it ends up in the sand trap all the time. So Schrodinger's equation is not the final word on this stuff. It's not relativistic. So it works pretty well for small atoms, but as your atoms start getting bigger and bigger, I think proton number around 20, calcium, you start seeing it breaking down, and then by the time you get to proton number 50, which is 10, up over here, SN, they can't use it anymore because the electrons moving around the atoms are moving so fast now, they're closing in on the speed of light. And Schrodinger's equation doesn't model that very well. So it's not relativistic, so it's a problem. And they knew that. They wanted, how do we get around this? It also, Schrodinger's equation, as it's written here, doesn't include particle spin. It doesn't know how to do particle spin. And that's what I'm going to show you on the next page. Again, too many equations, I know, I apologize. But this is really a history lesson. So we can kind of ignore the equations and just pay attention to the history a little bit. So this is all happening in the 1920s. Heisenberg came out with 2 papers in 1925. So the first one was all by himself, and the second one was with Max Born here and with Jordan. And these 3 guys together actually wrote these equations here. A times B is not equal to B times A, and the birth of what we call the commutator. So 5 times 6 equals 6 times 5, right? Well, these things can't be just simple numbers. They're matrices. And they were forced upon it. Heisenberg, famously, when he wrote his first paper, he showed Max Born, which was his advisor at the time, he showed him it, and he's like, when I multiply A times B, I don't get the same thing. What's going on? And physicists were not taught matrix algebra at the time. He didn't, Heisenberg didn't know matrix algebra. He didn't know what a matrix was. Max Born happened to see it. He happened to know what matrices were, and that's why they reformulated Heisenberg equations into matrix mechanics. It was forced upon them. You had to use it. It wasn't an afterthought. It wasn't, oh wow, this is cool, let's try nifty, let's try this. It was forced upon them in what they were doing. And this commutator here is A times B minus B times A. It's kind of the error if you do A as an operator, say you measure position first and then B is the velocity, the momentum. But if you flip those around, you get a different answer. That's not usual. You don't expect that. You know, if you're on the streets of Manhattan and you go 2 blocks east and then 3 blocks north, it's the same as if you go 3 blocks north and 2 blocks east. You get to the same point. That's not true here. You get an error. They end up at different spots. So the commutator measures the error in how multiplying these things in different orders come about. That's where the Heisenberg uncertainty principle kind of comes from. Quick note, this is the same Max Born with that probability rule, all right? So all this stuff happened in the 1920s. This was a miraculous decade. Before the 1920s, they called that the old quantum theory. Starting with the 1920s is when the birth of the new quantum theory, and it started with Heisenberg and Born and Jordan. These guys put together their stuff in 1925, but Schrodinger and old Al didn't like it. So Schrodinger said, no, I got a better way to formulate it, and that's when he put together his Schrodinger equation. And you go through a lot of work with it in the textbooks. Most physicists prefer this because you don't have to know all the matrix stuff. So, but again, it's non-relativistic and there's no spin. And in this formulation of Schrodinger's equation, it's a scalar. Psi is just we call it a scalar. That means it's a single number, it's 1 by 1, and that it doesn't include spin, but it's still a complex number. So 1926 was Schrodinger. 1927, Mr. Pauli comes along, and he takes Schrodinger's equation and he applies it to a certain situation, but he made one big crucial difference. So don't worry about the details of the equation. He changed it from psi to psi-ket. And psi-ket now is a 2-column vector. So A and B are complex numbers here. So it's like 5 plus I6 and then 7 plus I8 on the bottom of it. These describe the spin of the electron. So when Pauli showed this, then everybody started incorporating kets back into this, although they didn't call it kets yet. That came from this guy down here. Kets and bras, you can blame on Dirac. All right? So that was the big revelation from Pauli, is that you could include spin in addition to some other stuff that he was doing here, but you can include spin in this thing. And then Klein-Gordon came along and they said, hey, we know how to make it relativistic. Well, they really didn't. It was wrong. So this was 1927 also, I think. All right? And then Mr. Dirac, working by himself, he finally sat there. The story is that he was looking into a fireplace and he was envisioning a different way of making Schrodinger's equation relativistic, and he came down with this, and he realized the only way to make this thing work is if I turned A sub k, that's 3 different matrices, A sub k and beta, if I turned them into 4 by 4 matrices. Once you turn them into 4 by 4 matrices, then psi can no longer just be like a simple number anymore. It has to be a 4 by 1 column vector. So that he was forced into it. So the first part, the A and the B, are kind of like the A and the B up here. So it's the spin of particle 1. But then what's the C and D in here? Well, Dirac realized that this is antimatter, or he didn't call it that at the time, I don't think. But the second particle, this is the birth of what we call antimatter. You probably heard of antimatter on Star Trek, you know. But if you really take a particle of matter and a particle of antimatter and you put the two things together, they will annihilate each other. And this was only a theoretical prediction by Dirac, and I think it was in the 50s. I forget who did it, but they detected the first particles of antimatter coming from out beyond the atmosphere, coming down, and they could see it in a cloud chamber, and it was spinning the wrong way. It had the mass of an electron, but it was spinning the opposite way, and they knew that it had the different charge. They knew that was the birth of antimatter, and I think that guy won a Nobel Prize, but Dirac won a Nobel Prize too. I'm just not sure when. So again, this is really the history here. It's all in the 20s, 1925, 1926, 1927, 1927, 1928. So a lot of stuff happened in the 20s. Yes?
Going back about 3 slides,
Oh, okay.
if you don't mind.
Sure.
one more.
Okay.
Yeah, that one. At one point you said if you turn the light on or off in a room, it may, your words were, it may behave like this.
Oh, it almost always does. I mean, if I actually hook up a light to an oscilloscope that can measure it fast enough, you'll see a quick ramp up, but it'll go to a constant level. So let's say the 120 volt lights, I turn it on, it doesn't just get to 120 volts instantaneously, it ramps up and then it's there. So you model these things with ramps, and it's really an exponential growth until it hits its max. And then this would be the opposite. Say it's at 120 volts and I turn it off, it doesn't just go to zero instantaneously, it decays down. Yeah, and it's definitely there. You can measure it. I think the Mythbusters guys actually showed that because they were trying to measure, does it cost you more to leave the lights on or to turning it on and off, because you get surges in current. I don't want to, okay, so the rack here, that's really your history lesson on this stuff. Here are some examples of different V of X's, different potential energy landscapes. There's a parabolic well, and you can see how it's shaped like 1/2 kx squared, which is a parabola. There's the infinite square well. The force is zero inside, but it's infinite outside. So the particle is constrained inside. And then here is a Coulomb force. So this is like atoms in a crystal, and I'm showing multiple Coulomb forces. Each well here is one atom. This parabolic well, you have to talk about it. It's obligatory to talk about simple harmonic oscillator. Whenever you talk about quantum mechanics, you have to talk about this guy. This is the only one where the energy levels are evenly spaced. But in all of them, they kind of act like a ladder. You start at the bottom, and then you have to step up the rungs. So every one of them has a quantized energy. And as you step up the energy ladder, you're getting to higher and higher energies. It takes more energy you put into the atom to get up there. So I got a little bit more pictures on some of these guys. So in detail, here's the pendulum again. I guess I didn't say it. The pendulum is so familiar, you guys don't even think about it probably anymore. It's, on a clock, or it's a child swinging on a swing. So at the bottom of the swing, you're moving the fastest, but up at the top, your velocity goes to zero, but your potential energy maxes out. And the velocity actually reverses. It's going positive, 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 getting smaller, and then it hits zero, and then it turns around and goes negative and comes back. So that's what really goes on classically. So at high energy levels, again, I told you these things were quantized, n equals 0 through 3, and all the way up. They go all the way up to infinity. So at n equals 10, it starts actually the blue curve here is the probability curve, and it starts resembling the probability for a classical particle. But down here at n equals 0, the classical probability curve, which is 1 over the velocity, is at a minimum, but the quantum probability is at a maximum. So you can see again, I forgot to say this, you can see again that here's the wave function. Psi 0 goes with n equals 0, psi 1 with n equal 1, but then you have to square each one of these things. And then when you compare that to over here with the classical probabilities, you see there's a difference, a little bit of a difference, and then they start to agree as n gets bigger. So, yes?
This is for one particle.
Yes, it is.
If I were to have a second particle, would I have a separate set of psis for that?
Oh, yeah. It would have a separate set of phis. As a matter of fact, if you moved them very close, okay, you see that these sides here are like the limits. This is called the classical turning limit. If you move two of them next to each other, the particle in quantum mechanics could actually leak into the second one next to it. That's really weird. You don't expect that. So there's you see that small tail that comes out here? That's probability leaking out. You don't see that classically. So yes, you can put these things together. And we do. When you build transistors, you got all these things together. So speaking of that kind of stuff, it's really the Coulomb force that governs all the atoms. The Coulomb force is the force between the charges. And again, this is the equation for it, minus 13.6 eV over n squared. So if n is 1, you get minus 13.6, but then it keeps stepping up. So this is like minus, that's over 4, so that's like minus 3, then minus, this is over 9, so it's like minus 1 or just under 1, and so on. And they keep getting smaller and closer together. So as the gaps get smaller, it acts more classical-like. At the bottom, it acts more quantum-like. So again, you're like stepping up on a ladder. So everything below E equals 0 are bound particles. Everything above it are free particles. A little bit more, I'm just randomly I picked a parabolic well. It doesn't have to be a parabolic well. This is old Al's contribution here. Energy equals a constant times frequency. Well, this equation really come from Planck, but it was this guy who figured out how it really worked. And this is the one thing he won a Nobel Prize for. He wrote this paper first in 1905. I'm not sure when he actually won the prize. But what this is saying is that the energy of the photon is h bar omega, which is equal to hf. F is in frequency, it's in hertz, and omega is in radians per second. So it's kind of like meters versus feet. You don't care what units. H bar, that's the only difference between h bar and h. It's just a constant, okay? But this is the energy of the incoming photon. You take its frequency and multiply it by h bar, and you know how much energy it is. Well, if that energy of that incoming photon matches the difference between two of these energy levels, then the atom will absorb that photon. So in this case, that's the reason I use parabolic, is because it's a really simple formula for the energy of all these wells. So it's just the n plus a half times h bar omega. This omega is not the same as this omega. This omega is the frequency of the photon. This omega is the square root of would be the spring constant over the mass, but it's something different. Unfortunately, apologize, we're running out of symbols, and you constantly having to interpret what the hell's that symbol mean. So, and when it emits a photon, that energy, say it's up here in n equals 3 and it goes down to n equal 1, well then it better get me the difference between 7 and 3, 4 units, 4 over 2 h bar omega units coming out. So again, this is really what old Al did. He figured out how the photoelectric effect worked, and he won the Nobel Prize for it. So up until this point, this is weird, up until this point, everybody thought that the energy of an oscillating wave, of a wave going up and down, was its amplitude. So if I say the amplitude times sine omega of something, doesn't matter what's inside here. If I give you a function of 5 times sine of something, then the amplitude, 5 squared, is how much energy that wave has. So classically, we say that the amplitude of the sine wave is the energy, but that's a classical result. Here, this is what's so weird, it's the frequency of the photon that gives me its energy. That is completely different from what people were thinking beforehand. You've probably all seen this. This is the uniqueness of the spectral lines. Sodium, hydrogen, calcium, mercury all have different signatures. And that photoelectric effect that I just showed you, every time you get a photon coming out, it's going to give me just one of these lines. Just one of them, and depending on which lines you're going between n equals 2 and n equals 7, or n equals 5 and n equals 1, depending on which ones you're going between, gives you different lines out. So this is how you look at stars, and you can determine what it's made out of. Doesn't tell you how much. Doesn't tell you how much is in that star, but it tells you that it's made of different elements. So then you have to go through, and I think one way to do it is look at the brightness of these lines and stuff. you can figure out what percentages. So you figure out it's like 95% hydrogen, 3% helium, and then trace amounts of everything else. So that's really hard. I don't know how they do that, but I think it has to do with the brightness and maybe other techniques. But these things offer unique signatures, and that's how we know what they are. And they don't always have to be at the same frequency here. These things can shift around. So if the star is moving away from you, all these lines move toward the red. It's just like when you hear a Doppler effect with a train. Train's coming at you, the train whistle sounds higher. As it goes away, the train whistle sounds lower. Same thing happens here. These lines will shift up and down, so they don't always stay at these colors. But the relative spacing of them is what's important. That's what determines what the chemical element is. That's its signature. Quantization doesn't only happen in quantum mechanics. It also happens with your guitar. So you got a fundamental and frequency, and that means the nodes are locked at either end. So this is the bass end of the guitar, this is the nut end, and then you can get higher harmonics out of these things. I don't have time to get into these things. We're running a little bit late, but I want to get to these. Again, sunspots are kind of cool because this is when people first realized sunspots are magnetic. So if you can do a telescope and zoom in over here and you'll see just one line. But if you zoom in on, if it's rotating and the sunspot comes into your window here, you'll see it split into two lines and then recollapse into one line as the sunspot goes by. That's how Hale figured out that sunspots are magnetic. Now we're getting into the real meat of this thing here. So this is a really funny setup with funny magnets. It's actually not too bad, really. Neutral silver atoms, they have to be neutral. We don't want them charged. You put them in an oven, so it's spitting out silver atoms, all right? And then you put it through a collimator, which is nothing more than two pieces of tin foil with holes poked in them. All you want to do is try to make sure the line, it's a straight line coming out of these things. And then you get all these random orientations, and silver's got a special feature. It has one unpaired electron at the top, and that's what's giving it its spin. And as they come out, you expect all these different random orientations, and then it hits the photographic plate. So Stern and Gerlach proposed this experiment and then went and did it. So which one do you think they saw? Did they see the filled in one? Or did they see, how many people think you saw the filled in one? How many people think you saw the empty one? Nobody? Okay, I got a few. I got one or two for, it's actually the second one. So they saw this. Stern was not a believer in quantum mechanics. He thought it was wrong. He set out to disprove quantum mechanics. And when he did this experiment, the story is that he took one of his nasty old cheap cigars and he blew smoke on the photographic plate, and this image came out. Now this is a stylized image. The image they actually came out was pretty ugly, but you could see it. So, but we don't care about the blue lines really. All you care about is what's at the top. At the top and what's at the bottom here is where the magnetic field is concentrated near this point here. So that's this high magnetic field in the center, and as you get off to the edges, it's weak magnetic field. So that's why it's important that this thing has this funny shape. So, but all we're looking at is right in this region here. All the atoms, all the silver atoms coming out are all spin up, and we write it like this. Psi up is 1, 0. Now notice I'm not writing it like sine waves. I'm just writing this. This is called a vector notation. This is a ket. And psi down is written as 0, 1. Well, this seems really silly so far, but this is what's going on. And it's a two-level system because you take spin 1/2, you plug it into this formula. 2 times a half is 1 plus 1 is 2. You get two levels out. There's two outcomes. It's either spin up or spin down. Well, we can have others, but spin 1/2 is all over the place. And you can have mixtures of these things too. So in this case, what Stern and Gerlach saw was a 50-50 mix. They saw 50% of the atoms coming out here and 50% of the atoms coming out here. But I could have like A times psi up and B times psi down. And I can say, maybe I want 70, I can prepare it so I get 70% or 80% up and only 20% down or something like that. And I would write that as A plus B. Now I'm kind of saying A and B are real numbers here, but they are complex. They're complex numbers. And I used to call this the ellipse, the ellipse figure, but because it's Valentine's Day, we'll call it the kisses, okay? So another picture of a spin coming from this place here, and you can see it written in many different ways. Psi is A, B, and a column vector. You also see it written with h bars over 2. Those are actually eigenvalues, but I don't want to get into it. So I put this off later because I didn't want, most math books start off with all the definitions. I hate that. I don't want to see all the definitions, corollaries, all that stuff up front. Now go do the homework. So I put it later on because I've been using the words. So if I just write a 1 by 1 number, that's just 5 plus I, well in this case they're real, so just 5. That's a scalar, no rows, no columns. So if I write 5, 6, and 7 on 3 different rows here, that's a 3 by 1 column vector, but I could also have a row vector. And we write that as x is an element of real to the n, or in this case, real cubed. And then I could have a matrix. Now it's rows and columns together. So each one of these is a separate number, and rows by columns always is the way we do it. And that could be n times m numbers. So that's an element of this, of n times m. That's, again, mathematics notation. Now, this is all real numbers. Next I'm going to show you with complex. I like to think of an Excel spreadsheet. You got an Excel spreadsheet, you've got rows and columns, and every cell is a scalar, every column is a vector, and then if I put a whole lay out rows and columns all over the place, then I got a matrix. So think of an Excel spreadsheet, and I like to think of variables as shoeboxes. You don't know what's in the shoebox until you open it up. So a lot of times you're trying to figure out what that variable is. So here's column vectors. These are kets, sorry. Kets and column vector notation. People cheat, they just write psi a lot of times, or they write psi ket like this, and then that would be like A plus IB, C plus ID, and these are all real numbers. A and B, C and D are all real numbers. We're going to see it in this form later. This is spin 1/2. There are 2 complex numbers, so it's a 2-level system. There's 2 outcomes. It can either be up or down. This guy is a 3-level system because there's 3 complex numbers. This is spin 1. And mathematicians will write this as psi equal element of complex cubed. Or you could see it also written as psi is real to the 6th power, right? But this is a spin 1 system. It's all using, to figure out the number of outcomes from the spin number, you're using this, 2s plus 1 all the time. So spin 1.5, you plug in 1.5, you get 2 times 1.5 is 3, plus 1 is 4. So you got 4 complex numbers. So this is kets. Bras are almost the same thing, except now I put the dagger on. The dagger flips the sign, the conjugate flips the sign of the second thing, the transpose turns rows into columns and columns into rows. Again, this was forced upon them. When physicists started doing this stuff, they didn't know matrix theory. It wasn't taught to physicists back in the 1910s and 1920s. They didn't know about this stuff. So it was kind of forced upon them. And it's taken off since. Now we use it all the time. We're talking about matrices all the time as operators. But this dagger thing is really important. It's the transpose with the conjugate. Transpose turns rows into columns and vice versa. Conjugate flips the sign on the other piece. And you see now how I've written this on a single row, and I've written it in parentheses again. So that's why I put the little separators in there so you know it's 4 complex numbers here. This is a 1 by 4 complex. 1 row by 4 columns. 1 row by 3 columns. All right. Spin operators. Mr. Pauli here. We mentioned him before. He came up with the Pauli matrices. And these are operators. They ask questions, but they can also do things. They can also perform operations on stuff. And then I didn't come up with Hadamard picture. And identity just leaves things unchanged. It's important. We have to use it all the time, and we have to account for it. So here's my really super simple calculation here. This is Pauli X operating on psi up, and then sandwiched with psi down. You have to always sandwich the operator in between two wave functions. So here I'm going through the calculations, but I end up with just a 1. What is this thing telling me? So when I first learned this stuff, it was just rote memorization. You had to go through, do the calculations, and you come out with a number, okay? That was it. But there was no interpretation. What this is really doing, sigma x will turn out to be a 180-degree rotation. It doesn't look like it. That doesn't look like a 180-degree rotation to me or anybody else who's done any kind of stuff like that. Sigma x turns psi up into psi down, and then you're taking psi down dotted with psi down with 100%. Sigma x turns psi up into psi down with a 100% probability. That's what this says. Okay, it gets a little bit more complicated now. I showed you the parabolic well before. Every one of these states is one letter in the ket. So this n equals 0 is the A, and the B is n equal 1, and so on. And if you do A dagger A, that's kind of the probability of being in state 0. And B dagger B is the state of being in state 1. So you can think of it as, oh, I'm 70% likely to be in state 0, I'm 20% likely to be in state 1, and I'm 5% likely to be in state 2. So you can think of these all as probabilities here. And this is without spin, there's no spins. So if I add spins into each one of these things, it blows up even more. And this is already an infinitely long matrix, or an infinitely long column vector. How do you multiply infinitely long vectors? You know, when you're first trying to do that stuff, it's difficult. It's like, what are you doing? Well, you do it in pieces is what you do, and you only have to concentrate on you make certain assumptions, restrictions and stuff. So I threw this in because it's kind of relevant. There's two different kinds of spin. There's integer spins, these are called bosons, and there's half integer spins, 1/2, 3/2, 5/2. These are fermions. These are the regular particles that you're used to. Spin statistics theorem, statistics here really means probability. So the bosons are the force carriers. You've heard of these things. Higgs, you probably heard of Higgs and photons and gravitons. Well, that's 0 is, Higgs has a spin 0, photons have spin 1, gravitons have spin 2, and so on. They will bunch up. They will congregate. But fermions don't like that. They will not congregate. They must have unique state numbers. And those state numbers are NLMS. N is the total energy, angular momentum. I'll show you that in a second here. But you got 3 different statistics here depending on which kind of thing you're doing. This is only valid for Maxwell-Boltzmann, is only valid for classical stuff. Fermi-Dirac only applies to fermions. Bose-Einstein only applies to bosons. You can see they all are in agreement at very high energies, okay? So, but when they diverge down here. One other real footnote, this Maxwell-Boltzmann, this is in your, how many people use ChatGPT? I know you do. So you use ChatGPT. Well, turns out Maxwell-Boltzmann is actually in there. Okay, it's called the softmax function in that case. So a lot of the ideas in AI/ML came from physicists. Hopfield, well, you probably heard of Hinton. Hinton was on 60 Minutes a while ago, but there's others. So I just wanted to mention that real quick. So the spherical harmonics are basically, these are the orbital angular momentum. This is the summer-winter rotations on the electrons around an atom. So L equals 0 is always spheres. L equal 1 I call dumbbells or dipoles. L equal 2 are what I call quadbells or quadrupoles. All right, see how this is 4 lobes? and that's on the ends. So these are the M numbers tell you how much of the momentum is in the Z direction. And L equals 3, I call them hexabels. So see how there's 6 lobes here, and so on. These are probability clouds. It tells you where the electron is going to be. So again, that formula, 2s plus 1, well, now it's 2l plus 1. 2l plus 1 is 1, 3, 5, 7. If you double all those numbers, because you can put 2 electrons into each orbital, you get 2, 6, 10, 14. These are the numbers that determine the shape of the periodic table. This shape comes from these numbers over here. I'll show you a picture of that in just a second here. Another picture of spherical harmonics. So these two over here is at 7 by 2. This is rows by columns. So helium is over here because it acts like the noble gases, but you can also think of it as sitting over here, and some people do draw it over here. So this completes the S shell. So the S shell takes 2 electrons. Then the P shell can take 6 electrons. This is a 6 by 6 arrangement. And then the D shell can take 10 electrons. So there's actually 10 entries in here for 10 columns, all right, only 4 rows. And then finally, the actinide and lanthanides are 2 by 14. These are F shell. They take 14 electrons as you're going across. 1 electron here, 1 electron here, another one here, and by the time you get all the way down here, you've added the 14th electron down here. So really the shape of the periodic table, trying to get in time, okay. So putting it all together, the total wave function for atoms is the radial part plus the spherical harmonics times the spin 1/2 part. So this is really just multiplying them all out. Crazy formula for the radial part, crazy formula for the angular part. I'm not going to go into them. These pictures are coming from these things. So I like this table because it shows the N numbers, the shells, the subshells, the orbitals. Again, 2, 6, 10, 14 are the shape of the periodic table. Different story now. This is interference patterns, and this is where I wanted to integrate put all this stuff together. So if you got 2 waves and they're perfectly lined up, the 5 plus 5 double up, you get plus 10. The minus 5 and the minus 5 double up, you get a minus 10. So the height of this thing doubles. Constructive interference, they double the height. Destructive interference, they cancel out. 5 plus 5 with a minus 5 cancels to 0. And here you get minus 5 here, plus 5 here. You get a perfect flat line out. This is 0 height. This is destructive interference, they cancel. And it's all with a 1/2 a wavelength difference. So you've probably seen the 2 slit thing before. So if I have incoming plane waves, and these are crests, and I block one of the slits, I just get what looks like a Gaussian curve out here. It's maximum in the middle, right where the slit is. If I move the slit down, if I block it down here, then I get the same thing. It just moved up over here underneath this slit. So what happens if I unblock both slits? Which one do I get? A Gaussian? Huh? Do I get the Gaussian? Do I get the sinc function? Sinc function. You get the sinc function out. This is really strange, but you got to square it. So none of these negative values in here, they all move up to positive values. Again, it's probability. And so this is a real picture of what you get, and it all depends on the distances that you are away from it. So if I have, well, I was going to show you some numbers here in a second. This is a really wonderful picture. So you get right down the middle, you get a max. That's with this bright line here. But these black lines are destructive interference. These red lines are constructive interference. You get out light. The black lines, you get out no light. And so it's dark. So, but you get the same thing with sound waves. So these waves, this interference patterns can occur in any kind of wave. It really is universal. It can occur water waves, electromagnetic waves, sound waves, quantum mechanical waves, even gravitational waves. Anything that waves can do, constructive and destructive interference, they kind of act the same. So, but But now I'm going to do the same experiment now with an electron. What happens? If I have one slit covered up, I get out a Gaussian. If I have another slit, the other slit covered up, I get a Gaussian. But if I uncover both, which one do I get? You get the sinc function again. Now this is just a simulation, but this has really been done. You get electrons act like waves. They're particles, but they're acting like waves. This is the beginning of wave-particle duality. So, and I'd be remiss if I didn't mention it. So the opposite is also true. Waves can act like particles, and that's what Compton showed. And Compton was here. He won the Nobel Prize in 1927 here. The building next door to us is called Compton Hall for Arthur Holly Compton. There's a street down over here by Chaffetz called Compton Avenue. That's named for Arthur Holly Compton. And he was the first Nobel Prize winner here from WashU. So different kinds of antennas now. You got monopole antennas, dipole antennas, and spiral antennas. And they all look radically different, okay? So I like to think, let's start with the dipole real quick. I'm trying to cut through some of this stuff. Here is a simple dipole. And you've seen it, rabbit ears, right? So there's an insulator in the middle. They do not connect. I could connect a battery to these things through this connector, and this would be plus minus, or I flip the battery around, and this is plus minus. This dipole is the center one here, and it has a radiation pattern that comes off of it. Well, I'll come back to the radiation pattern. But monopoles are kind of the same thing. Monopole is just like a single dipole, but you have to have a dipole. So where is the other part to this TV antenna or this AM radio antenna? It's the Earth. The Earth acts like the other part of the dipole. And if in your car you have a monopole on it, it's the car body itself that acts like the other part of the dipole. So they all really come down to dipoles. Now circular is a little bit different. You see how the signal is injected in the center, and as it spirals out, the wave is now twisting as it's being launched. So you can get a right-hand circular or a left-hand circular. GPS and FM radios are actually circularly polarized. GPS for different reasons. TV stations are normally horizontally polarized, and that's why you get these up on your house, okay? And then AM radio stations are like this. This is a ground plane with this monopole here. Your router at home has multiple antennas. This is like that multi-slit experiment that I showed you. So each one of these acts like a separate slit. So if every one of these is transmitting a sine wave, then what you do is you get a bright spot on, say, the wall over there and a bright spot on this wall, because it doesn't know which way is which. But now if I delay it, so if this one's at delay 0, this one's 1 nanosecond delayed, this one's 2 nanoseconds delayed, this one's 3 nanoseconds delayed, I can move that bright spot around. That's what your Wi-Fi is doing for you at home. It's moving the signal around depending on where you are. It figures out where you are. It's way too complicated to go into here, but that's what it's really doing. So you can move signals around with multiple antennas. Wait a minute. I can write a horizontal dipole as 1, 0, and I can write a vertical dipole as, I have my other antenna in here. So I can have a transmitting antenna and I can have a receiving antenna. And these are both horizontal. If these are both horizontal, if I can get it to stand up. If these are both horizontal, when one transmits, the other one will receive it. But if I take it now and I turn this one so it's vertical and this one's horizontal, They don't connect. They don't talk anymore. This is just like the math that we just saw with Stern-Gerlach. 1, 0, and 0, 1. So this would be called 1, 0. This would be called 0, 1. They have a physical interpretation, and it works the same with your antennas. So here I'm going to do some quick calculation. We don't call them kets, though, in electrical engineering. They call them Jones vectors and Jones calculus. And you can plot all these points on a sphere. Horizontal, vertical. So again, horizontal, then vertical, and then you get diagonal is really just 45 degrees, plus 45 degrees, and then anti-diagonal is minus 45 degrees, and then you get those circular or spiral patterns, right-hand circular and left-hand circular, and you can put all these things onto a sphere. And these are some of the numbers that go with them. Again, they're vectors. They're 2 by 1 vectors, two rows, 1 column. And I was sitting in an antenna class and I realized that these things are the same. I'm trying to get done here. We're getting down to the experiments. Oh, and we are at the experiment. So I was going to show you okay. Turn on the audio here. Tell you what, turn it down a little bit. That's not too annoying, I think, right? So here we go. We can go horizontal. So it's just pointing straight up. And you can see this on the scope. So I'm really generating this tone, and it's only coming out here. So this guy is the horizontal. This guy will be the vertical. I sound like Outer Limits, don't I? So, and I go to vertical. And so now I'm just moving the dot up and down. The oscilloscope here is in a special mode called XY mode. And then I can go to diagonal. And now you see why I call it diagonal. So in quantum optics, we really call them these things. So anti-diagonal is the opposite. And the way I have it set up is that you're hearing perfect cancellation when it's diagonal, when it's anti-diagonal, and you're hearing it's doubling the volume when it's in diagonal mode because you're adding the two together. But that's just the way I'm doing it here. And then you finally get into a right-hand circular, and you see how it's spinning around, and left-hand, so it's spinning the opposite way. But let's go back up here to horizontal, and notice that the ket is straight up. It's on the North Pole. So if I come down here and I say poly X, this is one thing we showed before, it turns it into poly Y, it turns it into vertical. So sigma X turned what was pointing north into what was pointing south. That is what sigma X does. It was a 180-degree rotation. It took it from north down to south, and then you can do this, you can go back, so it just jumps back and forth. It's a 180-degree rotation. And poly Y kind of does the same thing. Well, that doesn't, what? And then poly Z doesn't do anything. What? That doesn't make any sense. Well, it's a 180-degree, poly Z is a 180-degree rotation, but about the Z axis. And if it's already on the Z axis, it does nothing to it. Poly Y is rotating about the Y axis, but it has the same effect. Poly X is rotating about, your thumb goes in the direction of the axis and it rotates that way. So that's what you're seeing happen here. These are the operators, and then I will leave you with one here. We'll go back north. I'm going to do the Hadamard, and it goes from north down to the equator. But I'm telling you, that's a 180-degree rotation. It's a 180-degree rotation, but about what axis? About the axis that's coming out at the 45-degree line here. So in between the X and the Z, there's a 45-degree line. It's a rotation of 180 degrees about that. So Hadamard, these are all the things that you use. This Poincare sphere is the same as Let me go back to the presentation. Poincare sphere is really, I was going to do in wavelengths, we're going to skip that now. Poincare sphere is the same as the Bloch sphere, but the Bloch sphere is only labeled with a 0 and a 1. Well, those are highly abstract. I don't know what those are. The first time I'm seeing it, I don't know what 0 and 1 are. I'm trying to figure out physically what do they mean. Well, that's why I like the Poincare sphere from quantum optics, because everything's labeled. I understand what every point is on that sphere. I can interpret it. I can set it up. The Bloch sphere just calls them 0 and 1, and you're done. A slightly better representation, though, is not the Poincare sphere or the Bloch sphere. Mathematicians call this CP1, complex projective 1. And really, you've got a longitude and a latitude. So latitude up and down, you got your longitude around, but now you have a twisting angle that tells you, so it's a flagpole that's sticking out. So you know the wind direction, but not the wind magnitude. So it's three things that you know. That's why this is probably a better representation of a quantum qubit and antenna patterns and stuff like that. So MRIs also use spin 1/2. Wonderful pictures. Go check it out on Wikipedia. And the final one I was going to show you is this one, but I think this is a quantum Fourier transform. I'll show it to you later. If you guys come down later, you want to see it. But I think at this point, we're going to say we're done. The only thing I wanted to leave you with is this quote. I love this quote. True voyage of discovery. So what you're seeing down below, these plots are of a thing called zeta, the Riemann zeta function, and it has 1, 2, 3 representations here, but there are more. What I want you to do is start thinking of yourself as an ant. Shrink yourself down to the size of an ant, and then you're walking through this landscape. There are peaks here, there are mountains here taller than Mount Everest. There are valleys deeper than the Marianas Trench. And if you shrink yourself down to an ant and you go exploring these things, you'll find that funny things happen when you encircle one of those mountains. Funny things happen. So there's so much more I could say about this, but we're going to leave it here. I love the quote, "Mathematics is your new eyes." Thank you.